very nice in March.
Go to the beach.
Yeah, we have to do a lot of stuff there. They have conferences. The arena can be many, many things. All right, part 2, reading guide 2. The only question I generally, okay, I'm going to start with you, CJ.
Number
3. Alright, so I'm going over reading guide 2. I hope that you're with me because, if you're turning this in and it's 100% correct, it's an easy read, okay? So matter is broken up into 2 big ideas or big categories. What are they?
mixtures.
Okay, mixtures and pure substances. And then this is kind of the map you're to draw. It said to draw a diagram or a map. Make a map of the types of pure substances and mixtures and identify each. So, yeah, it's about page 50. It's in chapter 2. So then after that, you could further break down mixtures into 2 categories and pure substances into 2 categories. What are the 2 categories of mixtures? Shout them out. Homogeneous and heterogeneous, or homogeneous and heterogeneous. But those are different types of mixtures. We're going to get to that next week. And then pure substances, what are the 2 categories? Elements and compounds. There you go. That's exactly what you had. Pat yourself on the back. Good job. All right, another question on chapter 2. Speak now for hold your peace. Yeah. Describe, what can you calculate using the law of conservation of mass? So the law of conservation of mass is matter or mass is neither created nor destroyed, so you can calculate the amount of products that should be formed. Let's say you have 1 gram of reactant A and 1 gram of reactant B, assuming the law is followed. We're good citizens, we try to follow the law, so does science. Where we take these 2 and put them together, we should make 2 grams of product. So usually the amount of products produced. Any more, guys? All right. I'm going to say in the next minute, make sure you're good with with everything, guys. Pass those up and over to Tessa. So dog ear the corners if you need to. Questions? Do you have a stapler here? Pass this back if you need to. I need those, but I'm going to just have these today.
Were we allowed to write on this today?
You were, but we're going to need some of the problems on there today. So, guys, do me a favor. Eyes up here. If you happen to write so the reading guides I know were here. If you write on this paper, hold on to this till the end of class because we're going to need some of these questions today. So don't turn that in until the very end, okay? So you probably won't be writing much on the side. I just like to have the questions in front of you because it's easier to see them on the board. Okay, so just make sure if you did write on that, don't turn it in right now. Test is only taking like another paper, and then you'll put them in the box on the way out. Oh, dang. Hold on. There's another blue stapler. Will you pass that around? Just kind of keep passing it if you don't need it. I have another stapler. Okay, so Tessa, just drop them on the side of your desk. I'll get those. I hope it works. If not, dog ear it. Yes.
Like I did give up.
I'm going to talk about that in 1 second, okay? Alright, so make sure everybody has a chance. Take 30 seconds to finish whatever you're finishing. I have 2 things I need to address. Labs and warm-up. It's empty? I see pink, or I see staples in there. No, I thought I saw red. You can just hold on to the high heel for a second, okay? Alright, so I'm going to do warm-up in a second, but for lab purposes, and if we get to towards the end of class and we have some time to go back to our labs to finish graphing and sending pictures of your organized density objects, that's going to be done today or Tuesday. So if you have your labs, hold on to them until Tuesday because I do want everybody to graph their results. We just didn't get a chance to yesterday because of the festival. So hold on to your stuff until Tuesday. Cool? Warm up. Okay, so density we are very familiar with. We have an idea of how to calculate it. We know how to employ sig figs in it. Now today we're going to work on converting using density. But before we do that, I just want to do a general density problem. I want to see how you guys would normally solve it. And then we're going to reflect on that at the end of the day and see how do you solve it with our new method that we'll learn today. Okay, so we see the density is 13.2 centimeters cubed. Is that dense or not very dense?
That's pretty dense.
Like super dense. Mercury is very, very, very dense. So this right here is called a conversion factor. And that is something,
in general or the grams per centimeter?
the fact that it has a fraction. The nature of this measure, or this unit, that it has a fraction in it, is generally called a conversion factor. And you guys already know what conversion factors are. I want you to tell me something that's an equivalency, okay? So if I say 1 foot, you say 12 inches, right? You know that. You know 1 foot is equal to 12 inches. If I said a dozen, 12, whatever, right? A mile, 5,280. Gee, I was looking for those.
Too far.
So basically, conversion factors are things that are equivalent. Okay. So this 13.2 grams. If I had a cube of mercury, okay, if I have a cube of mercury, and it was 1 centimeter by 1 centimeter by 1 centimeter, it would weigh 13.2 grams. So they're an equivalent kind of idea. So we're going to work with that more today. But before we do that, I want to see how you guys solve this problem, because it's probably different than what I would do using this dimensional analysis thing we're going to do today. So if a container needs to hold 125 grams of mercury, what's the minimum volume needed? What would you do, Josh?
I wrote out the volume density equals mass of the bottle.
Okay.
And then I just plugged in that I know 13.8 density.
Okay.
So it has to equal 125.
So would equal to the mass 125.5 grams over the volume, which is our unknown, right?
Yeah, and I just multiplied the two.
Say again. I don't know. 125. I'm thinking of another problem I did in another class. Sorry. All right, so 125.0 over volume. So then how would you solve for volume?
Multiplied the two.
You what? You multiply the two? That's going to give you a number that's too large. So if you're solving for something in the denominator, how do you pull it out of the denominator?
You can flip it. You can put the
So
lines up.
floppy dot, or whatever you guys call that.
Then
Floppy
you can
dot.
flip it.
Copy dot flop. Okay, so you could do that. I was going to say multiply by v on both sides. Okay, basically same thing, right?
A lot
Okay.
simpler.
So if you multiply by v,
Don't
and
do
then
anything.
multiply by v, these cancel, right? This v needs to be isolated. So then what do you do?
By 13.2.
Yes, divide by 13.2. So 125 divided by 13.2 would give you like 9, what is it? 9.47 units.
Centimeters cubed.
You know it's a volume, right? You know it's not the grams. It's got to be centimeters cubed. So use your logic there too. Okay, so I hear 9.47, and it seems as if we've already considered sig figs, right? 3 sig figs, 4 sig figs. We said that was the weakest link was 3 sig figs, so we recorded, I think it was 9.469.
Both those are 3.
This is a 0. That's 4, and that's 3. So then we have 3 sig figs at the end based on someone rounding for us. So in the end, I know you guys can solve by making a proportion and isolating a variable and going on with whatever algebra 1 nonsense this is and solving, okay? So we're going to learn how to do this in a different way today, but not yet, okay? Actually, who watched the optional video last night?
There was an optional
It's okay.
video.
It's to help you. So basically the way your brain works is the more often you see something, the more likely you are to remember it. I took this big class last year, and it doesn't matter if you study for 6 hours or if you study for 30 minutes for, how many days is that? 12 days. Okay, 30 minutes, 12 days is way better than 6 hours in one time. You will never remember everything in 6 hours. You always will remember things if you've seen them at least 3 times. So if you watch something at night and you go to sleep, your brain's still working and it continues to understand or attempt to understand what you watched. So, yeah, your brain works a lot harder when you're sleeping because it's not distracted. It's always distracted.
Twitter's not there when you're asleep.
Huh?
Twitter isn't there.
Yeah, really. So let's watch this right here. I have the video here. I want to show part of it so that it's a good introduction to what we're going to talk about now, okay? So if you can just pay attention, you don't need to write anything down. Pay attention. We're not watching Hillary at all.
A set of tools that chemists
We're not
use to
watching anything but
manipulate
chemistry.
quantities of substances. In working with chemical quantities, it is important to remember that each quantity has associated with it both a unit and a chemical substance. And it is important to always write both of these down. So, for example, we will write 4.1 kilograms of water, or 0.23 moles of oxygen, or 3.0 times 10 to the 21st atom sodium. Dimensional analysis provides us with the tools needed to convert between different units of measurement. Let's say we have the definition. 1 kilogram is equal to 1,000 grams. We can take this definition and form a ratio. 1,000 grams over 1 kilogram is equal to 1. And the inverse of that, 1 kilogram over 1,000 grams is equal to 1. These ratios are useful since...
Okay, so, I know, that almost fell. I always trip in the shoes. So, this right here is just a number and another number that we're saying is equivalent. We all know, because the King Henry died by drinking chocolate milk, that little prefix conversion number line system, we know that there's 1,000 grams in a kilogram. It doesn't matter if you write it this way or you flip it upside down and write it this way. Regardless, something that's equal to something else over itself is equal to 1. So whenever I say 1 foot is equal to 12 inches, is that really a different number? Is it really a different value? No, it's the same value. We just changed the way it looked. So that's what we're going to be talking about today, is we need to be able to converge easy things like this before we can understand the little bit more difficult things like chemistry, the terms of chemistry, are going to require of us.
They allow us to convert from quantities in grams to quantities in kilograms, and vice versa. Consider, for example, the quantity, 4.1 kilograms of water. And say we want to convert this quantity to grams of water. We begin by writing down our initial quantity of 4.1 kilograms water. Next, we multiply the ratio 1,000 grams water over 1 kilogram of water. Remember that above this ratio was shown to be 1, so we are just multiplying our initial quantity by 1. This multiplication does not change the amount of water. It merely changes the units we are using to describe this amount of water. This multiplication gives the value 4,100. To determine the units of this quantity, we cancel the kilograms water and are left with grams water. So we achieved our goal of converting the quantity 4.1 kilograms of water over to that same amount expressed in grams of water. Let's do another example of a unit conversion. Say we are given the density of water as 1 gram of water per milliliter of water.
Okay, so we'll finish that up, but overall, what was the one thing at the very end he said you could do when something was on top and bottom? The units were the same on top and bottom. They cancel, okay? So that's our goal today, is to make sure we're able to cancel units appropriately. So let's talk about dimensional analysis. Yes. Look, it actually exists. I didn't make this one, okay? All right, so that's what we're talking
You
about.
didn't make that?
Not make this.
That's one. Okay, who makes the ones over that way? Who makes the,
These are all teacher meetings.
interest?
Oh my gosh, late. So I'm going to be solving numerous examples. Make sure you're writing down samples of these so that on problem set 3B, which I don't know if you've looked at problem set 3B, but it's a beast. Okay, it's a beast. You are going to be doing half of it this weekend, okay? The other half will be due Wednesday. So if you wish to get ahead, go for it. But I would like for you to do half of it. So again, you're looking at the same kind of idea 3 or 4 times so you really understand it, okay? So the two words that are up here, they're really equivalent. The term dimensional analysis is chemistry math. In your book, though, you're going to see it called factor label method. Factor meaning like fraction, label meaning the units that you're using to label them, and then the method that you're using to solve. So generally, it is going to be including a lot of fractions, numerators and denominators, so we're all familiar with what fractions are. And then also using the units of our SI system that we're going to be talking about a lot, grams, meters, liters. So I'm going to start you off with one that's familiar called using density, showing you how I would ask you to solve a density problem. So again, my density that's given here, and this one's not on the paper I provided for you. This is some samples first. The example here says aluminum's density is 2.7 grams per centimeter squared, or cubed. That's our conversion factor. generally in a problem, you're going to find that you'll have something given to you called a conversion factor. And how can you really identify it? You're going to be looking for something with a fraction in it. You'll also be given something as a fact, some fact about the compound of interest or the problem. Sometimes in big word problems, it's hard to pick out what the fact is. It's usually like a singular number with a unit, of course. And then you're usually going to be given a question, because what else are you going to do with this information, right? The question here is grams. So that's my big question. I want to convert from centimeters cubed to grams. Well, the only relationship between centimeters cubed and grams is
Density.
grams per centimeter cubed, or density, right? So that's the use of density. It's the only way you're going to get from there to there. So the way you would do it is implement fractions versus proportions. So it's just another way to solve some of the problems you're already familiar with and some of the ones that are going to be new today. So if we have 40 centimeters cubed, this is a numerator, okay? So if you want to put it over 1, put it over 1. Just to make sure you're clear which is the numerator, which is the denominator whenever you write them across the board. So I'm going to multiply this by a conversion factor to convert it to the unit of interest. So what I need to do is this centimeters cubed, nobody cares about anymore, right? We don't want this. This has to go in the denominator in order to be canceled. Not the whole number, just the centimeters cubed. Okay? So it has to be counter to each other, so one numerator and one denominator for it to be able to cancel. The grams are what I want. So if you want it, you need to put it on top so it doesn't cancel. So when I put this on top, you'll notice that this is grams per centimeter cubed, which happens to be exactly the way this is written, as 2.7 grams per centimeter cubed. So that fraction is going to be put right here. 2.7 has to go with the grams, because that's what the density is. And if you want to put a 1 down here, just to hold the place, to show that you're dividing by 1, that's fine. But the big deal here is really that you can cancel your units. Centimeters cubed on top, centimeters cubed on bottom, cancel, and then now we can do the math to find the grams that 40.0 centimeters cubed would take up of aluminum. So that's why everybody has a calculator. So how would you do this math? Are you multiplying or are you dividing? You're just multiplying, right? So 40.0 times 2.7 is, say, 108. What unit is left here? Grams. So the only unit that we didn't cancel was grams, which means we need to keep that. Because I'm really getting good at taking attendance, but I'm leaving the alarm just in case. Okay, so 40.0 and 2.7. Ignore these ones for now, because they're not truly our measurement of this particular activity. The true measurement's actually the first thing here. So I'm going to ask you to do two things. This is how many sig figs? Okay, 3. If I want you to round that to 2 sig figs, what would you write?
110.
Okay, I get some consistency here. 110. I heard 10. I was like, no. Okay, so 110 would be 2 sig figs because there's no decimal, so the 0 doesn't necessarily count. All right, so that's the same thing as you guys doing the proportion. It really is. It's just all in one step versus like, let's take this at the bottom, let's, divide by this. We're using dimensional analysis. Yeah.
On like test surfaces, can we still do the proportion?
So you are going to be okay to use the proportion for certain questions, like that first warm-up we had. I would take that because you're just getting used to this. But you'll find that some of these really, you won't even think to use the proportion, but you won't know what to do. So then your second option is this. Okay? Yeah.
Is there going to be questions like this on the course today?
No. Yeah. So this is a really weird question because I'm not telling you necessarily all the information you need to know, but I just said this is the measurement. So truly, if I said this is the measurement, this is the only thing that has a true number of sig figs. This is a conversion factor. Sometimes our conversion factors are true measurements, like density can be, but other things that we're going to use later, like the metric system, we don't even look at the sig figs for the conversion factors because sometimes they're not really measurements. This one is, actually, density is a measurement because you measured in your lab yesterday. So this is the best answer. Yeah.
So when you answer in sig figs, do you look at like the answer that you get and either round up or down depending on whichever number it is?
Yes.
Okay.
I got every question. Okay, so let's do this again. Same information. 2.7 grams per centimeter cubed is like the conversion factor we'll be using. And I want you guys to tell me how this question changes how you write it. So start it with your given. Think about what you said to cancel. What's the conversion factor in this one? It's still the density. It's just up on top of the board. I know you can't see it. Don't forget, you can use that, okay?
So, do you have to keep the 2.7 attached to the grams?
Good question. You absolutely have to keep the 2.7 attached to grams because that's who it belongs to.
That's multiplying them together, so you have to keep it together.
Yes, because it's the 2.7, or the grams is describing the 2.7. So on this one, you guys started off with 40.0 grams, and then what did you write next? Take a stab at it. It's the first time we've ever seen this.
Centimeters cubed over 2.7 grams.
Good. So this right here, this conversion factor, remember like on the video, he flipped it in the video, 1,000 grams over kilogram or kilogram over 1,000 grams. This is flippable. This is a tool for you. Use it however you need to. So the 2.7 grams needs to go on the bottom because grams and grams have to cancel. And then the centimeters cubed does go on top because you're converting to space, which space is an example of volume. So then in this one, mathematically, what are you actually going to be doing? Right, so what's 40.0 divided by 2.7?
14.8 or something like that.
Can you give me like 3 decimal second around? 815, okay. Centimeters, is that what you got? Okay, centimeters cubed. Is this right? Let me double check that. Okay. So grams and grams cancel because those two units are counter to each other. No, you're not canceling the numbers, you are actually using them for calculations. So then 40.0 sig figs, 2.7 has 2 sig figs, 2 sig figs reigns. What's the final answer? How many sig figs did I just say? 2. Not. So some of us are going 14, right? But don't forget, you got to look at the 8, and it's like, nope, round that baby up, 15 centimeters cubed. Okay, so I'm modeling how I want you to show your work on problem set 3B. Don't gyp yourself. You need to make sure you're practicing with me, okay? So I'm going to try to cover maybe 1 or 2 examples of each main type of problem so that you have enough to work from for homework, and then you guys will work on that in class towards the end. Okay, I'm going to skip these right now. I'll come back because these are more complex. Okay, let me go back here. You guys remember this from the video a couple days ago? Yeah? Okay. I don't have some of the other ones on here. I want you to write this across the top of your paper, okay? King Henry died, how? By drinking chocolate milk, ... Yeah, so what's that something?
No, it's like
It's a U thing. It's not a U.
Backwards Y.
I know that, but what's it called? Micro, okay. So King Henry ... drink chocolate milk ... micro ... nano ... pico. That's a P. Okay. And then mega's on this side, right? All right. So this is going to be used basically the entire day. Okay. So that's what I want you to have at the top of your paper. All right. So if I said, all right, guys, how many micrometers? Where's micro?
all the way down there.
Well, you think, okay? How many micrometers are in a kilometer or a kilometer? A lot, right? So what I need you to do is think about it in terms of zeros all the way across. This is like a number scale of zeros. So what you do is 1 kilometer has a 1 next to it, okay? You put the 1 under the kilometer, and this is how you can think about it, but I'm going to just model it for you written out. And all you do is to figure out how many micrometers are in there is you make zeros go all the way across, including the decimals. So that's 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. How many zeros?
9.
9. Is that 9? Okay. So that's 10 to the 9th. That means 1 kilometer has 10 to the 9th micrometers in it.
It's not like a billion, or is that?
That's a billion, I think, yeah. So this is your conversion factor. Look, we just made an equivalency. 1 kilometer has a billion micrometers in it. That one's one you maybe just didn't know. Who knows that random information? Nobody. But what if I said, how many millimeters are in a meter?
1,000.
We all kind of know there's 1,000 millimeters in a meter. Proving it though, you can do exactly the same thing. Where's meter here?
Yeah, base.
Base, right? Because remember, base is meter, liter, and gram. Okay, base is meter, liter, and gram. So if you have 1 meter, it has 1,000 millis in it. Okay, so do you know how to use this now? We can keep practicing with it, but I want you to have it at the top of your paper for that use.
So then the way you would set up that ratio would be like 1 meter over 1,000 millimeters.
Right? Or
And
vice
then
versa.
It doesn't matter either way. Yeah. You can
Yeah.
flip
So once you come up with your own ratio, you write it the way you need to in your problem to solve for whatever you're solving for. Yeah.
So would there be 10 to the negative 9 kilometers
In 1 micrometer? Yes, but I really do hate negative exponents if we can avoid it, because most people are really comfortable with positive exponents. So I always say the 1 goes with the larger unit, and then the large number goes with the smaller unit, because you have 1 huge kilometer and lots and lots and lots of little teeny micrometers. I try to stay away from negatives. You'll see a couple in some problem sets, but I find that you understand this way, not the other way. Just my level of thought to help you guys, okay? So I'm going to probably do 2 from each of these sides. This right here is on the paper copy I gave you, the reading guide on the back, okay? So if you want to just kind of work me through those, I do recommend you write them on a separate sheet of paper, because there's not much room left on that little paper.
So what are you doing this weekend?
Oh man, we've got all kinds of house cleaning. It don't work.
Oh yeah, you're going. Got you had it.
I don't know what else we're doing.
So why are you going back to get a second master's?
It's my first master's.
First master's? Why are you going to get your first master's?
Okay, split.
Oh, okay.
Yeah.
I was like, there'd be no real reason to do it.
They don't pay us anymore. All right, guys, you with me? You with me? All right, I want to give you a second there when I get settled. I'm going to work slowly through 2 easy ones, and then I'm going to go down to ones that have multiple units in them, okay? So these are just metric conversions. So if I have 3,500, write that out. That's your only given here. 3,500.0 milligrams. You guys have your conversion factors in your number line. You have to come up with your own conversion factors for these because you have the metric system in front of you. So I want to go to grams, right? So on your number line, you're looking, is gram or milligram bigger? Gram, right? All right, so you're thinking about that. What unit do you know has to go on the bottom down here? Milligram, because you want to cancel it, right? You don't want milligrams anymore. It's out of the picture. So if you're converting 2 grams, it's the one that's going to go on top, because that's what you want. You got me on the unit so far.
Yep.
What's the relationship on your number line with grams and milligrams? So who gets the 1? 1 gram gets how many? 1,000 milligrams. So we can look across and we see those 3 zeros from G, which is a base, to milli. So, yes ma'am. You got it? Okay. So in your calculator, in your head, what you're doing is you're taking 3,500 divided by 1,000. Well, 3.5. That's what we say first, right? Then we go sig figs. All right, so I want you to only look at the sig figs for these numbers that are given to you, because you really don't have anything else to work with. These are simply conversions, this metric system stuff, whereas this was the measurement that somebody took on a scale to get that many milligrams. So how many sig figs are here? How many? 5. So what else do I need here? There you go. You are very, very, very specific. You're very accurate. You have 3.5000 grams. That's what that's related to, or that's what that's equivalent to. Done, right? So far so good? I see some people say shaking hands, but others not, so I want to make sure I keep working through. I'm going to 3, because I want to use this micro a little bit more with you guys. So 843.45.6 micrometers. So you got your initial, and we're going to meters, right? So we're going to meters. So King Henry.
You're in meters?
So we're going from micrometers to meters. So here's 6 zeros, right?
6 zeros.
So before I move on to like putting numbers in, can you guys tell me the units that are going to go here? That's going to go on bottom. Micrometer goes on bottom because you need to cancel it.
And you need a million on the bottom there.
So ain't nobody got time to write a million, right? We can't write that. You put 10 to the 6. Yeah, don't waste your time putting that many zeros because you're going to be counting the zeros. 10 to the 6 is just more efficient, right? So 1 meter, and the way we got that, if you're still looking at the number line, meters at base, that's 1 meter, and then you have to go all the way here to micro. So that's 1, 0, 2, 3, 4, 5, 6. These decimals count as placeholders. There are units that exist there. I can't remember what they are now, but you don't really use them at all in chemistry. So that's why those dots do count. All right, so that's a million. So you take 8 point blah 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 divided by 10 to the 6 in your calculator, and you should get, well, I'll write it in non-scientific notation for you guys. 0.084345.6. Is that right? How many sig figs does this one carry? 6. How many does this one carry? 6. Okay, you're right. Whoever said 6, thank you. So this 0 is not a significant digit because you see the decimals present, you start at the Pacific, you count the first non-zero, which is 8, not 0. So 1, 2, 3, 4, 5, 6. And then what's the unit here? Meters, because micrometers and micrometers have canceled. And I didn't cancel those here, but they canceled. Yeah. Because we went through and we said the relationship between micrometer and meter is base is meter, right? Micro is this guy over here. And you put the 1 at the biggest unit and you add zeros until you hit the smaller unit. And then so that's how many zeros we include. There were 6 zeros there, but instead of writing that, we wrote 10 to the 6. Okay. All right, first 2 examples. Give me 2 thumbs up if those are okay. Alright, I'm going to keep working through this slide then. I'm going to do one of the harder ones that still include only a single conversion. Are you guys back? Okay, so let's go down to 6. This one looks a little different because we start with a fraction, and that's just because I want you to see how you can have 2 conversions in one problem. So the first conversion, you can see we're going from grams to what in the other numerator? Kilograms, and we're going from milliliters to liters. So we're going to do 2 steps here. So basically, write out your first one just like you have been, 4.52 grams over milliliters. And let's just start with the numerator, and let's convert it first. Don't try to do both at once, let's just do one at a time. So ignore the fact that this milliliter is even here. So look at your number line. How do you get from grams to kilograms? Don't say it out loud yet. Okay, and then tell me the unit system here first. What's going to go in the numerator?
1 kilogram.
Okay, I'm just going to pick the units first and I'll put the numbers. So kilogram is going to be on top because I need to go to kilograms per my question. And you know grams has to go on bottom because the only way it's going to ever cancel. So then on your number line, you said, okay, 1 kilogram is the bigger unit. Kilo is 1. How many grams are in a kilo? 1,000 because you count your 3 zeros over. And then go ahead and cancel out your grams. Do not cancel your 1,000. Leave it there for now. We're not done calculating. Don't even whip out the calculator yet. Okay, so we've accomplished mission 1. It's to get kilograms. Don't touch that now. It's good. That's what we wanted here. So now we need to take this milli to a liter. And so we're going to stretch across back to the board to the very, very, very beginning and see that the milli is here on the bottom, right? I need to cancel that, right? So it's going to go on top. And then what's going to go on bottom?
Liters.
Right, liters, because that's what the question is asking for. And then you go to your number line, and you're like, okay, what's the relationship?
1,000 milliliters to a liter.
There's 1,000 milliliters in 1 liter, because liter is base again.
And then you can just multiply across.
Right, and this one's actually easy. Do you need to pull out your calculator? Wait, do you need to? Why?
452 grams.
So 1,000
Because the 1,000s actually cancel themselves out. So this just happened to happen that way. I wanted to show you that you could do 2 or 3 or 15 conversions in one big problem. But then you should try to make sure if anything can simplify, you do that first before you start plugging your calculator. Because you can imagine a lot of fractions and parentheses, your calculator can get pretty complex. So the milliliters and these milliliters do cancel. And then it just so happens 1,000 cancels with this 1,000. So then what's the answer?
4.52 kilograms.
Kilograms per liter.
They check
Just happens to be the same number.
That's one of those ones that works out too well, so it's like you're not sure if you got it right or not.
Yeah, I try not to trick you guys too much, so just be confident if you're confident. All right, look at the next set of questions.
Next.
What do you look at those and tell me which ones you feel like you're like, oh my gosh, I don't know how to do this, or you're not sure which one you're for. So I'm here in 4. The first ones, they're single. They say dual step or 2-step conversions because it says you have to go to base. If you're comfortable with going from mega to milli or mega to pico, you're just counting zeros across. Do that. You don't have to say, okay, let me take a breather at the base and then convert from base to the other one. You don't have to do that. Yeah. This one? We're in this little second set. So I'm going to start with 4, just because I heard that was a request, okay? So let's start with the hardest one. In this one, we have another, actually, do we have a 2-step conversion?
No.
No, we actually don't, because the hour stays the same. So the hour is not changing. We're not going to change the denominator. So let's write it out. 62.8 kilometers per hour. Anytime it says slash, I think it's in your best interest to write as a straight fraction, because then you don't have to worry about trying to figure out what's in the numerator or denominator. Okay. On your number line, touch kilo and centi, and I want you to tell me the difference or the number of zeros that connect them.
10 to the 5th.
Is it 10 to the 5th? Oh, hold on. What goes on the bottom? What unit goes on the bottom?
Kilometers.
Right, kilometers, because you don't want kilometers, so you have to cancel it here. And then centimeters goes on top, because you can see we're going from kilometers to centi. So we say 5 zeros connects them. So that's 10 to the 5th. Where does that go? With the centi, right. So 1 kilometer has 10 to the 5th centimeters in it. So lots of little units in it. So then that's going to be, you can just simply move the decimal 5 places or do it in scientific notation. So 62, 2, 3, 4, 5.
It's only 4 zeros.
1, 2, oh, sorry, I had extra. 1, 2, 3, 4, 5. My board is really off on this side, guys. Okay, so you can write it like this, centimeters per hour. Don't write it in a curve, I just write it in a space. But how could you write this in scientific notation as well to meet your required sig figs? 6.28. Okay, I heard somebody say 0 and then other people didn't.
Oh, it's 0.
0 times 10 to the 6. 1, 2, 3, 4, 5, 6, yeah. So you could write it like this to meet your 1, 2, 3, 4 sig figs, because this has 4 sig figs. This actually does not meet 4 sig figs, does it? Come here.
That's
1, 2,
7.
That's not a decimal.
Oh, that's not a decimal?
It looks like it was my erased 0. 1, 2, 3. There's only 3 there. These don't count as sig figs, so there's no decimal. Yeah.
So your answer always has to have the same amount of sig figs as like what it's asking you to
Convert only for these, because these are metric system ones, because the metric, this stuff in the middle, obviously if I was looking at this for sig figs every single metric problem, every single one of them would have one sig fig. Because that's one sig fig, right? And the metric system itself isn't a measurement. I mean, it's a measurement because it has a unit, but it's not something I measured. It just happens to be a really convenient way to convert. So yeah, for these metric ones, stick with the first number as your sig fig number. But later on, we're going to do ones that are a bit more involved. Yeah, let's see.
Why did you put the 10 to the 5 on top?
Because in this case, I was going from kilometers to centimeters, right? And so the kilometer here needs to cancel, right? And then in the end, the hour stays and the centimeters stay. So centimeters per hour were the units I was looking for. So I had to put the centimeters on top, and it happened to be 1 kilometer contained that many centis in it. Okay. All right. So let's do 10 minutes of practice before I move on to the next section. So who has problem set 3B in front of them? 3B. Either you have it on your phone, you have it a printed copy, or I have it right here for you. Oh, that's problem set 1. So you are capable of much of this first section.
So
Do not do
what
the
we're doing.
1 second. Do not do the ones with the squares or the meters squared to centimeters squared. The complex ones right here don't do yet. You might be able to do some like the meter. You definitely can do like 6, 7, 8, 9. But these right here don't touch yet. So you need to work on these 3 sections right now. And that's going to get you a good portion into halfway through. Okay? So use your time wisely. Take about 10 minutes. Wait for me. Work with your peers on your homework. So, sign out on the door. Take the key. Keys at your time.
There's some math reason
It's on the board. I'll make it a little bit bigger. Not yet. It's not in the correct scientific notation. I want you to use that though, because that's how the answer is recorded. I'll show you the answers are on the bottom. Look. You check your answers at the end. Don't give it to me yet because we're still using this. Hey, girl.
Yeah, I mean.
So you don't need to listen to music or anything right now because you got 10 minutes, and if you don't use it, then I'm taking it back. Okay?
So it's just 750 times 10 to the third.
What else?
Is it supposed to be scientific notation?
No, I said leave it like that. I know it's not written correctly in scientific notation, but leave it like that, and then go ahead and do your conversion, and at the bottom you'll be able to check your answers. Just because I have the current answer in accordance with whatever that says right now. Okay.
Right.
So,
Because there's not 10 to 9 grams in 1 nanogram.
So I'm gonna go grab
There's 10 to 9 nanograms.
you determine, right?
So the nanogram on the bottom.
You got number 1 yet?
If I said I if I said meeting,
I got the How did you cut it out?
You just tell us experimental and stuff.
Wait,
I'm right now this particular so it's concept that
So 10 to the third.
that's 1 billion. That's 7.
This is
Hey, Joey, I got
It's the same as 7.5. How did you see it? 7.5? No, 750 or 750
10 to the third, and then you convert the
So wait, how did you find 10 to negative? Like, where did you get 10 to negative 4? That's what you get when you make conversion. What? That's what you get when you do conversion.
So type in 750 times 10 to the third. Okay, so that's the number you're working with, how many nanograms you have currently. Then you're converting the nanograms into grams. So you just do the regular thing.
10 to the 9th nanograms to 1 And then so you divide or multiply.
You put grams on top, nanograms on bottom. So what? 7.5 to the negative 4.
So like this would all.
Yeah.
Okay, so
Scroll down. Oh, I don't know. Oh, let me wait. Let me see if imagine the 65 grams has 65 grams over 1. So we do divide. I don't know whether you divide. You multiply. 6.5 and then you divide. Or wouldn't it be 0.07 because there's only 1 segment? Oh, just kidding. Yeah. What? Yeah.
oh, but
0.065. Yeah. Yeah. That's a good question to ask yourself. Like, that's something that you would
I got it.
Oh, there's 1,000. Yeah. There's 1,000.
So how would you make that 360?
You could.
You could add a 0 at the end.
That won't work because the stuff don't. It's 4 seconds. What if you have to go 8.0?
Wait, what?
Two eights off. Zeros after a significant figure. What number was that?
That was. And then you have to go to site location. You cannot just say click. Just regular. Honestly, I confused the hell out of me like when we first started doing this.
Yeah, I didn't understand it first, and then I got it.
It's getting easier to do.
So then the bottom of the second. So for number 2, like it's a 65 grams. So like you might there's 1,000 grams and 1,000 kilograms. And that just times it by 1,000. So like 0.065.
And you can, and I'm able to listen to but the only reason how we do it is because there any some measurement and you can always, yeah,
That's supposed to be like an alpha.
yes, but it seems that it'll
I hate the really big ones.
yeah.
So you would do 8.80 times 10 to the third.
That's right.
Wait, this is actually starting to make a little sense.
That's pretty and look, on you, feeling I have to I just know all of you.
It would be 1,000. I just added 0. Same thing.
Divide. With the 2 seconds,
the one with the least amount of numbers in it, but that's more the highest number.
It also possible that adding and subtracting.
Yeah.
You always take the least divided by
The multiplication is always the highest.
it's always it's still the smallest number simplex. The thing is with addition and subtraction you count after the decimal point, and then with multiplication and division
It's just
it's just
that's so it's always the lowest.
yeah, it's always the
With
lowest.
adding, subtracting, decimal.
Alright guys, take a couple more minutes with where you are. I'm gonna give one example of the
That's not funny.
Yeah, so okay, so let's divide it.
It's confusing.
15 divided by 2.
I don't really like these calculating. I'm starting to understand the low number.
It's kind of like I see what why it's there.
Kind of sucks.
1.50. Answer saying that.
Yeah, right? Exactly.
There you are.
Answer 1.50.
Oh, and last year.
Oh wait, yeah. Yeah.
No, we got
How would you convert a nanometer to what's the point?
yeah, that makes sense. What is it? How small?
That's like DNA.
So yeah, no one can even that. You can't get stuff small.
It just doesn't make sense.
I would say like a step, like the closest to a step is probably
It'd be less than. Okay, yeah, a decameter. Is that the 100
that's
or
1/10.
Yeah, that's
Take 30 seconds.
very close to standard.
It's still not even.
It's still not.
It might be like 3 or 4.
Yeah.
With people with like 12 minutes. That's none of those.
Yeah. Like that would make sense.
is it?
It's saying, oh, we are right. You just don't have to convert it. You're right because the 0.0 at the beginning don't so it says,
Hold on. Why have all these alarms going off? Oh my god.
right now we technically be right.
Is that times echo? Is that the high one or the low one?
Low one. That's why you write them in little case or uppercase.
So low one's lowercase?
Lowercase is, I'm sorry, lowercase is deci. Uppercase is deca. Yeah.
8.8
Alright, back up here. 5, 4, 3, 2, 1. Okay, we have about 13 minutes left in class. I'm going to do one of these right now. So I want you to have a sample of it. So if you feel comfortable, if you're able to move on to those. I think a lot has got a number of them done. Very excited. Okay. So I'm starting with this one. This is back on the note sheet that I was working from earlier. If you're in the middle of a problem, I'm sorry, but be quiet so that I can make sure everybody sees this one. I know this doesn't look scary at all, but these ones with the cubed cubed units require you to cube all the conversion factors. So we're gonna have some cubes and squared things thrown around here, okay? Same thing we've been doing, except we're cubing things now. So write down this example with me so you have a sample. Take your 800.4 meters cubed, multiply, and let's just say ignore this cube for a second. Just pretend that little cube guy is not even there. Same thing on the question and answer up here. So if you didn't have this and this, what would you normally put right here? Centimeters and meters, and then what's the number that correlates them? 1 and 100. Okay. So if this were just a normal conversion, I know we said ignore the cube, right? Now we need to consider the cube. If you see the cube here, this meter must be cubed, and the only thing that will relate to a cube unit is another, well, not the only thing. Many times the cube unit must be related to another cube unit. But if the centimeter itself is going to be cubed, its number that's attached to it also must be cubed. So generally, I'll just put parentheses around it and say the whole shebang is cubed. Or if you don't like the parentheses, you're going to put 100 cubed and centimeters cubed. So either write 100 cubed centimeters cubed or parentheses 100 centimeters cubed. So I want you to plug it in your calculator because it's going to be a much different number than you would expect. So the meter cubed units do cancel. So that's going to be how many zeros is 2, 10, 6, so 1, 2, 3, 4, 5, 6. Is that right?
Yeah.
Okay. Centimeters cubed. So when you cube 100, that's 10 to the 6 zeros, right? Or 10 to the 6 making your multiplier. Now that does matter, right? Now, is this to correct sig figs? You say that so confidently. Yes, it is. Because where do you start counting your sig figs?
4.
So do you start at the 4 or do you stop at the 4?
Stop at 4.
Start at the 4. Okay, so you start at the Atlantic. There's no decimal. Decimal's absent. You start from the Atlantic. Skip. Start. 1, 2, 3, 4. 4 sig figs. 4 sig figs. So I feel like we practiced sig figs a number of times today. So that's the only thing that's different with these. For example, if you see squared, what are you going to do? Square the whole conversion factor, not cube it, okay? I'm going to leave that one to you guys, okay? So we have enough time. Do you guys want to look over anything before you take this quiz? I'll give you a minute to look over whatever you're looking over. Yeah.
I got to add up the decimal. Does it count 0
Don't count
Yeah, decimal goes from the only convert from the top.
Yeah.
So like 10 is only 100. 10, there's 2. Accuracy is how close you are to the actual true value. Precision is how close all of the values are together. That's easy. You're the same spot.
Depends on where the spot is. Is the spot accurate?
Times 25 bodies.
Let's say you consistently foul ball. What's that? Is that where you want to go? So let's say I'm fouling a ball, left field. That's like, you don't want that, right? That's very precise. You're precisely hitting it left field, but that's not what you want. You want a home run. You want to go there. So if you were consistently hitting home run, that'd be precise and accurate. So you can have both. I guess if you get like a home run every once in a while, it's not as All right, I think you've had your minute. Thank you. Please do two things